I'm Dave Oliver, Chief Meteorologist at KFDA TV in Amarillo. Being a television meteorologist, my most important duty is keeping the public informed during severe weather situations. That's why I know firsthand the importance of good, reliable information from spotters in the field. Spotters still confirming a tornado on the ground. It's about 7 miles north of the Texas state line that will be into the southern part of Texas County, about 12 miles southeast. I'm also an avid storm chaser myself and have been for many years. I've been in the midst of many a tornadic storm and experienced the awe and fascination of being near the power unleashed from severe storms. Now the storm you see is coming directly at us. This is about the 4th tornado we've seen from the storm. This one is huge. This would be about an F3 or F4 tornado. Severe weather is just a fascinating subject that many people find interesting. Most people want to learn more about storms, how they develop, and just what makes a tornado. And while most people in America try to avoid tornadoes at all costs, you may be part of that crazy group of people who have the desire to be right out in the middle of severe weather, to get out in the field during storm events to be a storm spotter. Some people have always wanted to try their luck at finding tornadoes, but just don't have the experience or knowledge of what to look for. That's what this field guide is all about. This is a short training session designed to familiarize people with severe storm behavior and how to recognize visual storm features associated with severe storms and developing tornadoes. This is not intended to be a complete severe weather training or an official certification program for spotters, but rather a basic introduction into severe weather and a supplemental visual aid for those interested in becoming official spotters or amateur storm chasers. Official certification programs are conducted periodically by local National Weather Service offices throughout the nation, and I strongly recommend these for anyone interested in severe weather spotting. As we begin, I think it's important to briefly discuss the fundamental cause of severe weather, and that is the formation of thunderstorms. Of course, not every thunderstorm will become severe, but having a large storm develop is certainly a prerequisite for severe weather. Meteorologists use the term convection to describe the process where air near the ground rises upward into the atmosphere. This upward vertical motion provides the energy to fuel developing thunderstorms. Here is a very basic description of the formation process. Warm, moist air near the ground becomes buoyant and rises. As the air rises, it expands and cools. Moisture contained in the rising air condenses into liquid drops, and a thunderstorm cloud begins to form. Within the building storm cloud, rain and hail are generated. This precipitation then falls back out of the cloud to the ground, along with cool air produced as precipitation evaporates. A thunderstorm can be divided into two basic components. Now, you have an updraft, where warm, energetic air is rising vertically up into the thunderstorm, and you have a downdraft, where rain-cooled air is descending back down to the ground. So you have air going up into the storm, and you have air coming back down out of the storm. And the differences are very great. For example, tornadoes are most likely found where the warm, buoyant air is rising vertically, a lot of energy in that area. On the other hand, in the downdraft is where you're most likely to find things like heavy rain, large hail, and turbulent winds in the downdraft area. The combination of an updraft and downdraft is known as a thunderstorm cell. Thunderstorms are not all alike. Some have different cell structures and behaviors. Different varieties of storms produce different kinds of severe weather, and some are more likely to produce tornadoes than others. Most storms consist of several cells, or several updrafts and corresponding downdrafts. These are called multi-cell thunderstorms. Most multi-cell storms are non-severe, but the strongest of multi-cells may occasionally produce large hail and damaging winds. Small tornadoes are not out of the question, but multi-cell storms rarely produce strong or long-lasting tornadoes. This is how a typical multi-cell storm may appear from a distance. Notice the number of individual cloud towers within the thunderstorm complex. Each tower is a separate updraft in a different stage of development. Cloud tower number 1, or cell number 1, is the tallest and oldest of the updrafts. It is reaching its peak in intensity, and that is where the heaviest precipitation is falling. This cell will soon begin to dissipate. Cell number 2 is growing and will take over as the dominant cell after the first cell dies. Cell number 3 is just beginning to develop, but will eventually be next in line as the dominant cell. This cycle of successive cell generation continues throughout the life of the storm. Individual cells last for about 30 minutes, and as each one reaches its peak in intensity, heavy rain and hail may be dropped to the surface below. The relatively short lifetime of each cell and lack of rotation in the updraft are the primary reasons that tornadoes are rare in multi-cell storms. A less common variety of thunderstorm is known as the supercell. Unlike the multi-cell storm, a supercell contains just one dominant updraft region. As the name implies, this is a super updraft, very intense and very long-lasting. A supercell updraft can, on occasion, persist for hours. The powerful, continuous updraft energy usually leads to the production of large hail, damaging winds, and frequently tornadoes. Supercell thunderstorms are unique in that they have the tendency to rotate. Now, not just a small, compact rotation like with the tornado, but a larger circulation, maybe 1 to 3 miles across, that may comprise the main portion of the entire updraft. Now, I want to make it clear that this video field guide was not intended to be a rigorous course in dynamic meteorology, but here's a simple demonstration as to why a supercell storm may go into rotation. The primary factor is the vertical wind profile in the vicinity of a developing supercell. In other words, how the wind changes with height. Here's an example. In a supercell situation, we often find the surface winds blowing from the south or southeast, but as you go higher up, say to 10,000 feet or so, the air currents may be from the southwest. Now, let's pretend that we placed a paddle wheel in this airflow. The southeast winds near the ground would force the bottom of the wheel in one direction, while the winds aloft would force the top of the wheel in the opposite direction. Now, this would set up a rotation, but it's about a horizontal axis, kind of like a bicycle tire. Now, this may be a little bit confusing because we all know that tornadoes don't rotate about a horizontal axis, but rather a vertical axis, more like a spinning top. So, how does the paddle wheel effect help to generate a tornado? Well, the trick is that the horizontal rotation gets tilted upward as the air accelerates up into the supercell updraft. So we now have a rotation within the large updraft, and it's called a mesocyclone. The transformation into vertical rotation is demonstrated in this computer animation. In the field, mesocyclones are extremely important for the spotter to identify because it is within these relatively larger circulations that most tornadoes form. In fact, virtually all tornadoes of strong intensity develop within the rotating updraft of a supercell storm. We will return to supercells and mesocyclones later, but now let's discuss how to identify the region of a storm that is most likely to produce a tornado. Since tornadoes are most likely to be found in the updraft region of the storm, that's priority one for the storm spotter: locate the storm updraft. Keep in mind, however, that other weather dangers like flooding rains, microbursts, damaging straight-line winds, hail, and lightning, all of those could be found in the downdraft region. In no way are we downplaying those weather events. In fact, we'll discuss the downdraft in detail a little bit later on. But for now, let's focus on the storm updraft, where tornadoes are most likely to be found. The updraft region of a thunderstorm can be identified easily, even if the storm itself is well off in the distance. Recall that the updraft is warm, buoyant air rising upward, sometimes explosively. This is where billowing cloud towers grow to great altitudes, perhaps 50,000 feet or higher. The distant updraft cloud tower normally resembles a huge head of cauliflower looming above the horizon. At the top of the storm, the rising air loses its buoyancy and flattens out. Strong upper-level winds then spread the cloud top downwind, forming the classic anvil shape to the cloud body. A dark area of precipitation or downdraft region may be visible just downwind of the updraft. It is underneath the rising updraft cloud towers, however, that tornadic activity, if any, will be found. Mobile chasers and storm spotters try to zero in on the updraft. So with this storm, we try to get under this area where you see the billowing cloud towers going up. Now, so far, our discussion has been limited to storms well off in the distance. Of course, to monitor for tornadoes requires a much closer vantage point. But before moving right underneath a severe storm, I think it's important to discuss a few safety rules, especially in the area of positioning. Storm spotters certainly need to be near enough to a storm to be able to monitor the most active part of a potentially tornadic storm. Very importantly, however, spotters must know the movement of the storm and have easy access to escape routes away from the storm's path. In other words, you want to be in a good position to be able to see tornadoes, but at the same time, you don't want to be trapped in harm's way. I mean, you don't want to be out on a road that dead ends as the tornado zeroes in on your location. So try to have escape routes available that can take you out of harm's way in case you have to bug out quickly. Severe storms usually travel toward the east or northeast. There are exceptions, of course, say with southward moving storms along a frontal boundary advancing from the north. Most severe storms, however, especially tornadic ones, are steered by upper-level winds which most often blow from the west or southwest during severe weather events. Big storms move along in the steering flow and generally travel from southwest to northeast. Generally, it's a good idea for the storm spotter to stay on the south side of a storm and move eastward, staying just south of the updraft as the storm travels downstream. This provides a clear line of sight to the updraft area while not being in the direct path of the storm. Photographers may prefer a location that is south and a little east of the storm. This is because more sunlight is usually available west of the storm, and this provides good contrast for taking pictures. Attempting to plunge into a storm from the north or east is much more dangerous. Coming in from these directions means plowing through precipitation, which can be unbelievably intense. The interceptor can suddenly find zero visibility in blinding rain and possibly destructive hail. The result can be an experience similar to this.
Probably golf balls our tail at this point. Road's almost completely covered.
Penetrating the storm blindly can also lead to a sudden confrontation with an unexpected tornado. Spotters should plan intercept routes that allow good line of sight into the updraft while avoiding the discomforts of heavy and dangerous precipitation. As we've seen, locating the updraft of a distant storm is simple and pretty basic. You just look for the big booming towers going up in the distance. It is when a menacing storm closes in and spreads directly overhead that storm spotting really begins. This is where smaller cloud features and important storm details are found that need to be monitored for possible tornadic development. The rain-free cloud base is the primary target for storm chasers and spotters in the field interested in watching for tornado genesis. The rain-free base is very significant because it identifies the underside of an updraft tower. The tower itself will be billowing to great altitudes above, but the bottom of the updraft tower is flat and dark. Despite the darkness, the base area is relatively free of precipitation as little rain falls here. This is because air from below is rising rapidly upward into the storm updraft. Precipitation forms at higher altitudes but is swept away by winds aloft and deposited downwind of the updraft. This is why heavy rain shafts are usually visible just downwind and adjacent to the rain-free base. Even though the precipitation area may appear darker and more threatening, it is the upward motion into the rain-free base area that is necessary for tornadic development. Since it is air rising vertically that fuels the updraft, there should be further recognizable signs of uplift in the rain-free base area, signs that help you identify the updraft. Often, small detached clouds called scud form beneath the storm and ascend up toward the base. In very powerful updrafts, the scud may rise quite rapidly. With some storms, uplift is readily apparent by simply watching the cloud base. There may be a suction-like effect visible as moisture condenses and shoots up into the cloud at base level. In this example, the explosive uplift of air is plain as day at the updraft cloud base. Updrafts are constantly being fed by warm air inflowing into the storm. Finding the inflow to the updraft is important because this is where tornadic development, if any, will be initiated. With most severe storms, inflow winds are from the south or southeast, pumping warm, moist air into the updraft region. In this example, we're looking north, and notice the grass. We have a warm wind at our back blowing towards and into the storm. This is the inflow. If we had a rain-cooled, chilly air blowing out from the storm, hitting us in the face, we'd know we had outflow and needed to adjust our positioning to find the inflow. This is a common development near the main precipitation area, but may also occur on the back edge of the storm. The so-called rear flank downdraft may cause cool air and precipitation to wrap around the updraft from the west. This can cut off the inflow and also restrict your visibility. Watch as this tornado disappears from sight as rear flank precipitation wraps around and obscures the funnel. This is why you generally want to stay south and a little east of the updraft for a good line of sight while still in the inflow area. In some of the most intense storms, the inflow winds may be incredible. Strong inflowing winds may suck dust off the ground and pull it skyward up into the updraft. The inflow into this supercell storm, for example, is marked very conspicuously by a large amount of incoming dust. Such an event sighted in the field is usually a good indication that you've located the hot spot for possible tornadic formation. Here's another example of dust being pulled upward into a strong updraft.
A word of caution with dust, however, is that blowing dust is very common in the outflow region of the storm as well.
While tornadoes are rare in outflow areas, blowing dust is often kicked up along the leading edge of rain-cooled air, blowing turbulently outward from the storm. The obvious difference, though, is that outflow dust is pushed out away from the storm, while inflow dust is pulled inward and up into the updraft region.
Once the inflow and updraft regions of the storm have been identified, the spotter can then watch closely for smaller detailed signs that may be indications of a developing tornado.
The favorite cloud feature among spotters and chasers, I would have to say, is the wall cloud. A wall cloud is a portion of the rain-free base which hangs down lower to the ground. Usually found near the interface of the updraft and downdraft, a wall cloud may stand out like a sore thumb as it juts down conspicuously toward the ground. There's a great deal of uplift in the wall cloud area, and along with the inflowing warm air, rain-cooled air from nearby precipitation may also be sucked upward. The rain-cooled air has a higher relative humidity and condenses at a lower altitude. This creates the low-hanging wall-like feature. The condensation of moisture may also extend from the wall cloud well back toward the precipitation area. This produces a horizontal extension of the wall, known as a tail cloud. Wall clouds are quite significant because the majority of tornadoes form within or very near a distinct wall cloud feature. Here you see the classic rain-free base, wall cloud, tornado structure, common with supercell storms. It should be mentioned, however, that not all tornadoes drop from noticeable wall clouds. Here, for example, is a tornado descending from a flat, rain-free base, but there's no apparent wall cloud. On the other hand, not all wall clouds are tornado producers. I've had film rolling on many a wall cloud that never produced even a funnel. When sighted, though, the wall cloud is certainly noteworthy because it marks the most active area of the updraft. The key to monitoring wall clouds is persistence. The longer a wall cloud exists, the more significant it is. Many wall-like features form and dissipate rather quickly and harmlessly. Long-lasting, well-defined wall clouds are more likely to be associated with tornadic activity.
Obvious signs of rotation in the thunderstorm updraft are critical signs that this may be a potentially tornadic thunderstorm. Rotating supercells comprise only 2 or 3% of all thunderstorms. So when you can notice rotation, that should be an alert that this may be a particularly dangerous storm.
Mesocyclones, or rotations in the storm updraft, may exhibit definite curvature near the base of the updraft tower. Circular striations, or a smooth, rounded texture to the cloud, may also be evidence of a rotating updraft. The curved cloud base may have a horseshoe shape in some mesocyclones, while others are more circular or ring-like. In some mesocyclones, the cloud may be rounded yet appear hollow in the center. This mesocyclone has a definite vaulted appearance, almost as if it has an eye. On an even smaller scale, rapid rotating motion may be noticeable within the cloud, especially in the wall cloud area. You may actually be able to see the cloud circulation twisting around and rotating. Not many sights are as ominous and fascinating as a low-hanging wall cloud that is obviously whirling around in rotation. Rotating wall clouds are red flag indications that a tornadic circulation is becoming established and a touchdown may be imminent. Discovering the presence of rotation in a supercell storm is certainly important, but perhaps the first unmistakable sign of an actual tornado forming is the development of a funnel cloud. The existence of a funnel means that a tornado vortex is at least beginning to become established.
Keep in mind that the goal of storm spotting is valuable lead time and the warning of people in danger. Sighting a funnel before it touches down and becomes destructive can certainly help to save lives. This is why accurate identification and reporting of funnels is so important to the warning process. The key word here is accurate. The spotter should be very cautious as to what is being reported as a funnel. Inexperienced cloud watchers have the tendency to report any dangling cloud fragment as a funnel. I guarantee that if you look hard enough at any storm, there will usually be some cloud feature that looks something like a funnel.
The fundamental guideline with funnels is rotation. True funnels always rotate. If the feature you are watching is not in rotation, it's probably unimportant.
Most of these false funnels and dangling cloud fingers don't last long before dissipating. This is why the spotter should take time to make a correct identification before reporting. Real funnel clouds will be more persistent. Not only are they longer lasting, but the real funnel will also be quite distinct with obvious rotating motion.
Funnel clouds, of course, are obvious indications that a tornado may be forming, but storm spotters should not get in the habit of watching only the cloud base for something hanging down. The fact is that watching the ground directly beneath the storm is just as important as watching the base of the storm itself.
When a tornadic circulation begins to materialize at ground level, dust and wind-blown debris may be picked up and whirled around within the developing circulation. An obvious swirl of dust on the ground under the rain-free base, then, is a clear-cut sign that a tornado is organizing. This dust whirl may coincide with a funnel that is becoming visible, or you may even see a swirl of debris well before there is any sign of a funnel hanging down from the cloud above. In this example, swirling debris still clearly indicates the presence of a tornadic circulation even after the visible funnel dissipates. The storm spotter should always remember the definition of a tornado, which is a violently rotating column of air descending from the cloud and in contact with the ground.
The key point in the definition is that the tornado is a column of air and not necessarily the visible funnel that you can see. This visible funnel is simply condensation of moisture within the tornado column. Sometimes that moisture makes it all the way down to the ground, and sometimes it doesn't. Now, whether or not the moisture makes it down to ground level is really unimportant as far as winds are concerned. Anytime you can see a swirl of debris on the ground, it's an unmistakable sign that that vigorous rotating column of air is indeed in contact with the ground.
Tornadoes come in a wide variety of sizes and shapes. No two tornadoes are quite exactly the same. Although all are dangerous to some degree, some tornadoes are much larger and more powerful than others. Smaller tornadoes may be tall and thin, sort of needle-like. Other small funnels may be long and skinny like a strand of string. They may twist and bend or wriggle like snakes. Even large and powerful tornadoes may diminish into a thin rope stage shortly before dissipating. You may encounter odd-looking funnels, like this one, that resembles a snake that has swallowed a rat. The classic tornado shape is that of a definite funnel or cone shape. Here is a common funnel-shaped tornado dipping from the clouds and ripping across the countryside. Some funnels may have more curvature than others. Some seem to be leaning to one side instead of standing straight. Some tornadoes, called multiple vortex tornadoes, have several smaller funnels rotating within the parent tornado. Multiple vortex tornadoes can be extremely destructive. Then come the big, ugly, giant tornadoes, which may grow to be more than a mile wide. Many storm chasers refer to these massive monsters as wedge tornadoes, since they look like a large wedge touching the ground. Ironically, the largest and most deadly tornadoes may be the most difficult to recognize. Massive, violent tornadoes are often written off by spectators as just big boiling clouds on the ground. These boiling clouds, however, are the ones that turn out to be wide-path killer storms. Along with differences in size and shape, color is another variable characteristic. Depending on the availability and direction of incoming sunlight, most tornadoes appear quite dark, say gray or even black. A tornado may, however, look very light in color, even whitish, if it is receiving sunlight while heavy precipitation is in the background. Tornadoes turning across dirt fields may entrain huge amounts of airborne dust in the circulation, creating a distinct brownish tint to the tornado. And a funnel may be very faint if there is precipitation and or dust occurring between you and the tornado. These are the tornadoes that can sneak up on you since they are obscured and difficult to identify. Tornadoes are certainly enough to worry about, but there may be other cloud features that can be recognizable signs of other storm dangers. Many of these non-tornadic storm hazards are found in the downdraft area. Remember, the downdraft is the result of rain-cooled air that becomes heavy and dense and subsequently plunges to the ground. At the surface, the descending air spreads out turbulently and pushes out away from the storm. The leading edge of this rain-cooled push of air is called the gust front. Tornadoes are rare along this abrupt wind shift. However, dangerous straight winds, possibly in excess of 100 miles per hour, may occur behind the gust front. Fortunately for the spotter in the field, these turbulent wind shift areas are often marked quite clearly. Here, from a distance, you see what is called a rain foot, where the heavy precipitation and cool air is striking the ground and spreading out horizontally. High winds are often experienced in the rain foot area. More commonly, the outflow gust front is marked quite clearly by a very noticeable cloud feature known as an Arcus cloud. The Arcus cloud develops as cold air from the storm cuts underneath the warmer air out ahead of the storm. As the warmer air overrides the colder air, moisture condenses, forming a long shelf-like Arcus cloud. The Arcus cloud steadily moves out away from the storm, staying just ahead of the precipitation area. Sometimes quite menacing in appearance, the Arcus cloud may also be accompanied by emerald green, turquoise, or pinkish colors. As the Arcus cloud sweeps by a location, there is a sudden wind shift, followed by a blast of rain-cooled air. High winds following the passage of the gust front often stir up dust, reducing visibility. Straight winds are often responsible for property damage, especially to mobile homes. Spotters should learn to recognize the gust front and Arcus cloud and consider finding some kind of shelter off the roadway during the peak of the turbulence. On a smaller scale, localized downbursts of air called microbursts can also generate destructive winds at the surface that can be destructive. Microbursts are caused by cool, negatively buoyant pockets of air crashing to the ground and are nearly impossible to identify in advance. As the small downburst slams into the ground, however, dust is usually kicked up in the turbulent area. The effect may be similar to that along the gust front, but with a microburst, the turbulent area is more compact and localized, not along a sprawling, well-defined wind shift line. As we mentioned earlier, tornadoes are rare in the downdraft gust front area of the storm. There is, however, a tornado-like phenomenon that occasionally forms along the gust front. Sometimes small and relatively weak circulations called gustnadoes can become established along or just ahead of the gust front. As the warm air ahead of the storm is lifted by the rain-cooled air cutting underneath, there may be enough uplift to support one of these gustnadoes. In comparison to full-fledged tornadoes, though, gustnadoes are usually quite weak and short in duration. Spotters should be aware that there are certain non-tornadic cloud features that can be mistaken for actual tornadoes. Tornado lookalikes, you might call them, that may really be something else. Mammatus clouds, for example, are often incorrectly reported as funnel clouds by people with little spotting experience. These pouch-like mammatus formations form at high altitudes on the underside of the high-level anvil. Mammatus are often associated with severe storms, but may be present with non-severe storms as well. In any event, they are not funnels, they do not rotate, and are not indications of tornadic activity. Be cautious of other false funnels and tornado lookalikes. Ragged appendages and cloud fragments along or behind the gust front are often reported as funnels, especially at night. Even though a little finger or tail may temporarily have somewhat of a funnel shape, watch it closely for rotation. True funnels will always be rotating. If the feature you are watching is not clearly in rotation, it is probably a harmless appendage that will dissipate shortly. Low-hanging Arcus clouds, like this one, are frequently mistaken for wall clouds. Remember the difference. Arcus clouds spread out away from the storm and move along ahead of the precipitation. Wall clouds are usually more compact and stay put beneath the updraft. We mentioned that a swirl of dust may indicate a developing tornadic circulation. Keep in mind, however, that dust is also stirred up in the outflow area along the gust front or in a microburst area. Once again, outflow dust will blow outward away from the storm and will normally be blown horizontally by the straight winds. Dust in a microburst may curl upward a little bit, but will not rotate about a vertical axis like a tornado. In the all-important wall cloud inflow region, dust is sucked into the storm and may rotate if a circulation is becoming established. Recognizing rotation in the cloud is certainly important for identification of mesocyclones and rotating wall clouds. The spotter should realize, however, that curvature to a cloud does not necessarily indicate a rotating updraft. Here, for example, you can see a strikingly rounded curvature in the storm, very similar to some of the mesocyclones displayed earlier. But this is simply a gust front Arcus cloud with layered, rounded edges. As expected with a gust front, the Arcus is propagating outward ahead of the rain and is not part of the updraft, nor is it actually rotating.
While cloud features and storm behavior are monitored pretty easily during the daytime hours, at night it's a different story. It can be a lot more frustrating and certainly more dangerous.
Finding and following features like the rain-free base, wall clouds, and funnels can be tough when you are relying on occasional lightning flashes as your source of light. Even the largest of tornadoes can be difficult to locate and track when there just isn't enough light. Sometimes the flashes from power lines or the audible roar from a tornado may be the only indication that danger is near. While intercepting storms at night, it is easy to be engulfed in heavy precipitation or to be caught too close to a developing wall cloud or tornado. In my opinion, amateur storm chasers should head for home after dark. It's just too dangerous when you can't see well. Community volunteer spotter networks, on the other hand, must still attempt to monitor storms as they approach populated areas at night. It's a tough job, and one must just be as careful as possible.
Storm spotters and chasers should realize that some storm hazards are always present, every time you go out, regardless of whether it's day or night.
Lightning, for example, accompanies every thunderstorm and can be an instant killer. Keep in mind that in open country, you are likely to be one of the tallest objects in your area. Some spotters opt to stay inside their vehicles as much as possible for protection. If you're in an area where the lightning is really intense and frequent, you might consider backing off to a safer position. Large hail can also be a hazard that strikes suddenly and puts you in danger. When watching storms, be wary of precipitation areas that may harbor big hail. You sure don't want to be caught far away from your vehicle when a barrage of hail strikes, nor do you want a broken windshield. A quick escape route is critical, so try to stay near roadways that can lead you out of the swath of hail. Overpasses can come in really handy. You might want to have one in sight if possible. When zeroing in on a storm, be selective about your route. If you are considering a dirt road, keep in mind that heavy rain may have fallen earlier on the road and you risk being stuck and stranded. It's better to lose a little time on a slightly out of the way but paved road instead of trying to dig out of the mud as a rotating wall cloud zeroes in on your vehicle. Even on paved roads, difficult as it may be when trying to catch a tornadic supercell, watch your speed on wet surfaces. Hydroplaning off the road can immediately ruin any storm intercept.
Intercepting storms and studying severe weather in the field can be a very fulfilling experience. I hope this video field guide has sparked your interest in the subject and helped familiarize you with severe storm behavior and spotting tips. I also hope you understand the dangers that go hand in hand with storm spotting. When you take to the field this storm season, be careful. Good luck and happy hunting.